Our very, very last lecture in physics is about inductance. And this is what this is all about. It is extremely difficult to measure magnetic flux. It's very hard to measure flux. It's hard to measure the magnetic field strength. But if you want to predict an EMF in a coil, we can do it if we know about the current in the coil. And what very, very common device can you measure current with? An ammeter. Every physics lab has an ammeter. So as long as we have an ammeter, we can measure current. And this is why we want to figure out how the magnetic flux relates to the current in a solenoid. Notice that we have a solenoid is just another name for a coil. We have yet another name for that today, an inductor. An inductor is the same thing as a coil, is the same thing as a solenoid. We typically refer to them differently depending on what they are doing. So we are going to start talking about inductance today. The whole idea of self-inductance is this. Well, let me ask you this first. If I had a coil and I took a bar magnet and moved it in and out of the coil, would I get an electric field? If I was changing the magnetic field, I would get an electric field. Would I get an EMF? Yes, you would. No matter what's happening, you'll get an EMF. That is just the integral of the electric field dotted on a completely circular path or a complete loop. Would I get current? That one depends. What's got to be there to actually get current if you have a changing magnetic flux? You need a conductor, and you also need a complete circuit. If you have a conductor that just has nothing connected to it, it's an open circuit, just a coil without the ends connected, you don't get current. The EMF will be in the same direction, just like it's trying to create current, it's trying to keep the flux close to being the same. It may not succeed if there's no conductor with a closed circuit. So any changing magnetic flux, phi B or phi B, however you decide to pronounce it, through a loop creates an electric field and an EMF. And the thing is, it even creates this when the changing magnetic flux is due to the current in the loop itself. You don't need an external magnet or a separate coil to get a changing magnetic flux. This coil that's right here, if you turn on and off the current in that coil, first of all, will you get a magnetic field in the coil if you turn on current? Yes. In fact, Easter Bunny, the magnetic field is equal to mu naught little n, the number of turns per unit length, times the current in the coil. That is the magnetic field.
And the magnetic flux through the coil is just that magnetic field times the cross-sectional area of the coil.
And if you change that current, you will be changing magnetic field and hence changing the magnetic flux. Here's how this works. If you've got a source EMF and I close this switch right there by connecting those two, I will start getting I'll get a current in that coil there. I will also start getting a magnetic field, and therefore I will get a changing magnetic flux. Here's what I want you guys to do. With this coil that's indicated right on here, I want you to tell me which way is the EMF that is produced when I close that switch. So that was you should be able to do that from the last unit. Which way is the EMF that is induced in that coil when I close the switch? I want to know not the EMF due to the battery, but I want to know about the EMF due to the changing magnetic flux. Go ahead and give that a try, and then we'll discuss how to do that.
Which way are you moving the bar magnet?
So I am not moving a bar magnet at all. All I'm doing is turning on this, just closing that switch right there. That's all I'm doing. This is the positive side of the battery right here. Right there's positive side. There's the negative side. I'm just closing the switch. One hint is the switch starts open. What's the current in the coil when you start the switch? When it's open, rather? Nothing. Then you close the switch like so, closing it, creating a complete circuit. Figure out which way the induced EMF is going to be. Go ahead and do that right now. And you can discuss that with someone next to you to help with that. Here's what we have to do to figure all that stuff out. We've got it starts off with no current. What would you do with your thumb if there's no current in this coil? Make it go away. No thumb. But then we start current. When we close that switch, current starts going through that coil, and that is going to look like this. Notice that it's going to curl around. If this is your coil, it curls around first the back of the coil and comes around the front. That's the direction of positive current. So once the current's going, the magnetic field will be which way? To the right. So we start off with nothing, and we end up with this. So which way is the change in magnetic field? To the right. Nature does not like a changing magnetic flux, so it will try to oppose that.
With a flux.
And then it will create an EMF that is trying to go this way. Now, you guys, is that in the same direction, or is that opposite to the EMF caused by the battery? That is in the opposite direction of the EMF caused by the battery.
So we very often indicate the EMF as if this coil were a battery. As the current is increasing, there is a back EMF with this polarity. The positive side of this coil is on this side, the negative side is on this side. It's pushing against our source EMF. So we very often mark our coil like this. Now you got to be careful though, because this coil will only have this polarity pushing backwards while the current is increasing. It does not like a current to change at all, so it's going to push against whichever way the current's changing. If the current's increasing, it'll push it backwards like this. There'll be a back EMF with this polarity.
So this is why we call this a back EMF. It's called a back EMF because it is in the opposite direction typically as the applied EMF. And one other reminder, flux is a scalar, but we can keep track of the positive or negative with our directional thumb. So I just when you're using this law, you're kind of cheating because you're using a direction to indicate a scalar magnitude, whether it's positive or negative. Just wanted to clarify that. Okay, so what we get is what is called a back EMF. The symbol for that back EMF is this thing right here, EL. It's a curly E. It's an EMF. That little L is the symbol for an inductor. It's a back EMF, E sub L, produced by a changing current in the coil. The reason you get an EMF when you change the current in the coil, because changing the current in the coil produces a changing, you could say magnetic field or magnetic flux. It's because a changing current produces a changing magnetic field in our coil.
One way to look at an inductor is using this analogy. An inductor is like this old crotchety guy, maybe a little bit like me. He's got an L on his shirt, and L's not for loser. L stands for inductor. And this guy works in a factory, and he stands all day by this tube that's filled with fluid. And he just hates any kind of change in current through that tube. So right now, all the water or fluid in the tube is at rest. He's fine. He's like, okay, this is the way it's been. I want it to stay this way. I don't want any change. Then some joker comes along and turns on the source pump, some pump that's going to start moving this water through the tube. And the pump is set up so when you turn it on, this becomes high pressure side and this side becomes low pressure, just like positive and negative of a battery. So that would start to push water through this way. So like a current would want to start going around clockwise. But this guy says, no, I don't want the current to change. So what he does is he turns his inductor pump on, so it opposes it. So there's high pressure on this side and low pressure on this side. So for that first instant, he actually prevents any current from flowing. And actually, he's fueled by any changes in current. But soon, this source pump starts winning, and the current starts to get higher and higher and higher through here. However, the rate of change of current starts to decrease, and his pump starts getting weaker and weaker and weaker. Or you can think of it as he just starts turning his pump off slowly. And so finally, after really infinite time, he says, all right, I'm settled then. I'll just deal with this current. This current's going to flow, and I'm going to deal with it. And I just want it to stay the same. I just don't want it to change at all. I want the current to be constant. But then all of a sudden, somebody turns off the source pump. And he's like, no, I don't want it to change. So he will start his pump up so that it pushes current this way. So this side will be high pressure, the right side, and the left side will be low pressure, so that it keeps the current going. And for that first instant, it will remain the same current, but after a while, the current starts to decay and it goes back down to nothing. And the inductor pump, unfortunately, can never win. It can only fight any changes. So after a while, the current just decays down to nothing. And he's like, all right, I'm happy with nothing happening again. I'll just keep it the way it is like this. So in other words, this inductor man, he just hates any change in current. And he will adjust his inductor pump so that changes in current are minimized. He tries to fight any change in current.